Welcome to another Tech Stuff Tuesday. This week we're going to talk about supercapacitors, when you would use them, why you should use them, when you shouldn't use them, how you assemble a bank of them. We're going to go over all of that stuff and have a little bit of explanation of all of these applications. What we've got here is definitely an excess power supercell from emfcaraudio.com. This particular example is 2.85 volts. There are other versions of capacitors. One thing you can look at with them, even the same between the same make, is they may have a different voltage. It might be 2.7 or 2.6, 2.5. And we'll get into why that matters. Then we have the capacity is 3,150 farads out of this one capacitor. Years ago in the past, you may have had somebody say, I have a capacitor, and it might have been a 1 farad. And it would have been a little bit larger than this. Around the same diameter, maybe a little bit larger and just a little bit taller, and it was 1 farad, and it was intended to be used on a 12-volt system. Now, those are essentially worthless in car audio. If you have a high current draw, those can actually cause a loss of power at the amp. This gets completely depleted, and then you end up having a low voltage scenario. It's trying to level out where your source coming in is, and this is a buffer. It completely depletes this. So you have low voltage on this end where the amplifier might be, but on this end, the charging side, where you might have lights and that kind of thing, where all of a sudden this is not dimming as badly, giving you the impression you're actually doing something. But in reality, you have lower power at the amp, which is not affecting performance at all. So we don't really see those too often anymore. We don't use them anymore. They generally don't work. Sometimes they'd be 2 farads, same kind of thing. And if you actually check capacitance of those old ones, you might find that are labeled 1 farad actually has something else in the canister, and it was not actually 1 farad at all. It may have been much, much, much less, and those go with the cheap things. You get what you pay for, that kind of thing. So we don't use those. This is the newer technology with the super capacitors. So on these, like I said, it's 2.85 volts, but we need it to operate on a 12-volt system. And the 12-volt system, you're going to charge around 14.4 volts. So what we're going to do is we need enough of these wired in series to be at a usable level. So we're going to use 5 of these. And if you do the math on that, you're going to come just under 14.4 volts. Now that's fine, because there actually is a little bit of a tolerance in these. I believe it's 10% that you can safely go over. People have said that you can go over that. I don't recommend that. But going to 14.4 volts with a 2.85 volt capacitor with 5 of them in series, you can do safely just fine. So first things first, we need to identify the positive and the negative side of this, because you do have to observe polarity. That's very, very important to this. I know on this already, this is positive, this is negative. They look different. There's markings on it, so you want to make sure that you're looking for any positive or negative markings on it, which on the excess cells is there. So we have to consider that. Another consideration, these were charged. They've been sitting for about 3 years, maybe a little bit more. But that being said, capacitors will discharge over time when they're sitting, and they do it very slowly. But this one still has 0.61 volts on it. Now, 0.6 volts doesn't sound like much. A AA battery has 1.5 volts. However, these have an enormous amount of energy being stored that can discharge very, very fast, way faster than you would a AA battery or any other battery like that. So even though this is 0.6 volts, if you dead short these 2 terminals or anything like that, it will spark, and it might even weld things together depending on what it is. So you want to make sure that these are as discharged as possible. You might have 0.1 volts when you pull it straight out of the box. That's very common. But like I said, these are 0.6. I won't be surprised if the rest of these are around 0.6 or 0.5. So we know positive, we know negative. So we're going to start. This is going to be where we're going to connect our amplifier and power, that kind of thing, into it. on one end there. So to wire this in series, we take another cell, this being the negative, this being the positive. That will go like so. We have bus bars. So these are very critical in what you're doing. The more material you can have, the better. Up to a certain point, there's going to be no return. If this is 1 inch thick, it's not going to do anything more than a 1/2 inch thick. And these are about an 1/8 inch thick. These will work pretty well. A little bit thicker wouldn't be bad depending on the current draw that you've got, but these do work out pretty well. These are aluminum. Do not use steel. Steel is not as good of a conductor. Aluminum works out pretty well. It's fairly economical. Or you can go copper. Copper does work better on caps. It doesn't seem like a whole lot when you're comparing the same size and everything, but it does make a difference at a higher cost. So we will get these connected. We have a lock washer and the appropriate nut. And you want to make sure that you get these torqued appropriately, not so light that it does not hold or it'll vibrate loose, and not too much to where it strips it. So on these I go to about 1 or 2 ugga chuggas, and it seems to work just fine. So now that we have 2 of these are our connection points. We can now see (1.22 volts) because we put these in series. So every time you put it in series, your voltage will increase. However, your capacity does not increase. It actually goes down. We'll get to that as soon as we get one of these completely assembled. So now that we've got one of these, we need to add another one. Positive here, negative here. Same thing as the other one. And now we have our negative over here, but we have a positive on the other side. So I'll show this with 3 cells. And we have 1.24. So we didn't gain a whole lot. This cell itself was completely discharged. This cell may actually be bad. It would have to be tested. It would be inconsistent with the rest of these, showing extra voltage. But we have to recharge that to see. But we are going to continue adding 2 more cells to this until we get 5. So now we've got all 5 of these together. We've got our negative down here, our positive down here. If we did banks of 6, both of these would come out on top, which can be a little bit easier depending on what it is that you're doing. But if we check each cell individually, we've got 0.6, 0.6, 0 as we saw before, 0.46, and 0.2. So when we do this all in series, this should average out, and we've got 0.57. So it's down a little bit, but we've got 0.57 volts across this whole thing. Now, because we're using the 2.85, when we charge this, it will charge at the voltage that you do it at. If you put it on a charger itself and you put the charger up to 12 volts, it will hold 12 volts. You take it off, it will maintain that 12 volts. If you have it at 14.4 volts in your car, when you shut the car off, this will stay at 14.4 volts, provided there is no draw on the system. So that is one beauty of the caps, is whatever voltage it is that you're charging at, or you store them at, that's where it natively wants to go. So when you've got a bunch of draw, if you're using a battery, it's going to want to bring down to where the battery voltage is. So your alternator is depleted. All of that amperage that you're putting out, can't put out anymore. You're down to say 13.0 volts, which is where the batteries rest. Now you're really into the battery power. With capacitors, because they're wanting to rest where you had it, you don't have that draw. So all the voltage that the alternator was giving it is going to maintain a higher voltage. The downside to this is you don't have the overall capacity. So from an amp hour standpoint, you might have a group 31 that might be 100 amp hours. These will be nowhere near that. 100 amp hours means you can put 100 amps on that battery for 1 hour, and it will go to 10.5 volts or so. That's the complete discharge rate. So it'll go from 13.0 to 10 volts, completely depleted. Not good for the battery when you do that, but you can put 100 amps on it for an hour to get to that point. These won't do that. These you can put 100 amps on it with no charging going into it, and it's only going to last seconds. It's definitely not going to last an hour. So how do we figure out the actual capacity of this bank? Well, like we looked at before, these are 3,150 farads each. With capacitors, 3,150, you actually divide between the number of cells. So 3,150 divided by 5 is 630. At full capacity voltage, 14.2 volts, these will provide 630 farads of storage. If you have less voltage, you actually have less capacity as well. So you want to get as close as possible to maximizing the voltage. When you have 2.85, you want to have 2.85 volts per cell to get the most capacity out of that as well. If we had 3,000 farad cells and we had 6 of them, that would be a 500 farad, because we're taking 3,000 divided by 6, that's 500. So we have 630 farads right here, where in the old days, this would not even be close. You would have to have 630 individual ones of these that are slightly larger to get 630 farads. So where would you use these? Well, one bank you could use in a musical application. I like to recommend 1,000 watts of amplifier power. You can go as much as 2,000 watts and still be pretty good. You might have 1 volt, 1.5 volts of drop. So for 2,000 watts of amp, you can use this on musical setup and you'd be in really good shape. For every 2,000 watts that you have to add one more bank of these. Fortunately, we have the ability to make more banks of these. So let's say this bank is good for 2,000 watts, but we've got a 6,000 watt amplifier. We've got to make 3 of these banks. So we're going to repeat this same thing 2 more times. So now that we've got 3 individual banks assembled, we need to get these paralleled. And when we do this, we're going to gain the capacity of the 630 times 3, and that's going to be the entire bank as it is in capacity at the voltage that we put into it. So because we've already started doing individual banks that we tie together, there's 2 different ways that we can do that. One, we could do 1 bar that we have made, so we have spaced out for each individual post. 1 giant bar covering as many as we need. In this case, it would be 3. So we'd have 1 bar that goes from here to here to here with holes, and we would secure it. Or, because we have a bunch of these bars already, we're just going to connect 1 to here, another from here to here, And then on the positive side, we'll do the same thing. And that's sparking because these are going to neutralize. One of these banks is lower than the other. So that's another reason to do this while discharged. We're going to put up with a little bit of sparks here. Now I've got the positive side, all three connected, the negative side, all three connected, and we can check voltage. And we now have 1.7 volts. So some of these, as you saw from the sparking, were charged a little more than the other ones. So we've got 1.7 volts across all of these, and this could be connected. Now I said there were two ways that we can connect all of these cells together, and this is still the existing that we've got, but the other way that we could do this is going to require a little bit of imagination because I don't actually have the things made to do this. But if we connect each of these together, we would have these in parallel. So picture this as one solid bar. One bar that connects all of these. So all of this would be one giant piece. And what you're accomplishing there is you're getting each one of these in series, but they're also in parallel. So the advantage to that would be you have a whole lot more surface area. You can get a whole lot more current through there. You don't have to worry about that. You could use a little bit thinner material in doing that. That can make for very easy connections across the board. You have fewer small pieces happening there. The disadvantage to doing that is something that I did not talk about with doing these individual bars, which would be load balancing. There are load balancing bus bars that you can put between these caps, and what those will do is prevent one cell from being overcharged. So this one might be slightly higher on charge than this one, so you continuously put voltage in. This one will stop charging. This one will take the energy that would be going to charging this one and it will charge this one instead. So you get all of them at equal charge, which is supposed to give a better performance overall because you don't have spots between here and here where you might have some uneven balance from current draw. Depending how well you've got these paralleled as well and all your connections, that can make a difference. In my experience, I have not really used load balancing. I have not found a need for it for burp applications. Once you get everything charged, and it will kind of balance itself out over time. But in a daily application, you might want to use load balancing just for your own protection, but also you can give a little bit better performance. From SPL, some might argue that load balancing does make a difference. I personally haven't seen it myself. So now we've got our bank assembled, and we can use this. And we're going to say that we're going to have our positive connected here, our negative connected down here, and this is in the car, but we haven't put power to it because remember, this is not charged. This is 1.7 volts at this point. Before we can have any use of this, it needs to be up at 12, 13, 14 volts. If you put a smart charger on this, one that you pick up a lot of times where it will sense how much charge is on it, and then it will dial that back, so not manual where it just keep charging it. If you put one of those on here, it's going to say this is a dead battery. It's probably not going to charge it. It might start to do it for a few seconds and they'll freak out, won't charge. So there's two ways you can go about this. One, you can put a manual charger on it and observe the voltage till you get up to at least maybe 9 or 10 volts. Then you can probably put a smart charger on it and it's going to work. The other option, if you have a charger that will do 6 or 12 volts, you can put 6 volts on this. And even a smart charger might be okay on the 6 volt setting. So once you get 6 volts, it's actually going to charge up to about 8. At that point, you can then put a 12 volt charger on it. And I've had success doing that, where even a smart charger, you can put 12 volt setting after it's got 8 volts or so, and it will work. If you're doing manual charging, make sure you're constantly monitoring voltage. You definitely do not want to just assume it's going to charge so much over a certain period of time. You definitely want to watch it all the time and make sure it does not get out of control. You do not want it to go over 14.4 volts at any given point. So now we've got this charged up, we've got it in car. Now, why would you want to use caps? Well, in SPL competition, you need a lot of power in a very short period of time. And these can deliver power much faster than a battery will. That has to do with internal resistance. They have a very, very low internal resistance. So we can deliver a ton of power in a short period of time, which is perfect for SPL burps. Where you would not want to use this is where you need a lot of capacity. Maybe you have enough alternator power to keep up, or maybe you're going to play it with without the car running for a period of time. These do not have that capacity. You're not going to want to use it for that purpose. If you're looking to save weight, this has a substantial weight savings over a battery. A battery of this size would be probably closer to 80 or 90 pounds, where this is going to be closer to about 20 pounds. So you have a significant weight savings and the difference in doing caps over batteries. Because we can configure this in any way that we want, any shape, form, we can turn these. They don't have to go in a straight line. These two could come over here. We can rotate them, orient them however we need to. You can fit these into really peculiar places that you couldn't fit a battery that's one static shape. These you can put any orientation, upside down, sideways, however you want. So whichever way works best for you, you can make this work. Now, if you're doing solid bus bars, you're kind of limited there. But for when you're doing individual singles, we can manipulate the shape however we need to, and whichever way you need to fit. If there's a spot that this shape that's very narrow will work for you, you can slide it in one spot. That works out perfect for that application. Remember, this is completely configurable where you can do this. So we've talked about all the plus sides of these. Now the downside is going to be cost. These do cost significantly more than an AGM battery. However, it's still less than a lithium battery. So that's a consideration when you're looking at the weight savings and the performance gains. If you don't need the amp hour capacity, then this is definitely worth spending the extra money for something like this. Now, maybe you don't want to configure all of these individually. You like the idea of the caps, but you want it in a battery case. Well, we offer those on emfcaraudio.com. Those are from Excess Power. They come already in the case. Any battery size case that they have, we can put caps in them. So we can have a Group 31 that has 2 banks of these in there. So that's kind of like the equivalent of having the power delivery of 2 Group 31s, but in the size of one case. So we are taking up less space for that power delivery. Or even in the smaller cases, like a D5100 case would have one of these in it. So you can get more power out of that same case size. Those also have all the load balancing in those, so you don't have to worry about any of that stuff and still getting the best performance possible out of that battery size case. Also, with those cases, you have the benefit of having only one positive and one negative to deal with, and you could take out a battery that has an amp rack, bus bars, or anything already built for it and put a bunch of these caps in that place because the case is the same. If you like this video, give it a thumbs up. If you have any questions or comments about super caps in general, or any questions about how this is laid out, you can leave those comments below. You can support us on Patreon. The link for that is also below. And you can also support these videos and the store by shopping emfcaraudio.com. I'll see you again in another Tech Stuff Tuesday.